Hello students, this lesson is on trigonometric functions. Now suppose we have a right triangle, such as here. A triangle has three sides, forming three different angles. We have an angle here whose measurement we'll say is alpha, so that could stand for 10 degrees, 20 degrees, 30 degrees, etc. We have an angle up here, which we're not focusing on for this slide, and then we have an angle down here whose measurement is 90 degrees. And it's the fact that one of these angles has a measurement of 90 degrees that makes this a right triangle. Thus, these two legs are perpendicular to each other, and this longest side is called the hypotenuse. Now let's focus on this angle over here, whose measurement is alpha. Relative to that angle, this leg of the triangle is called the adjacent, because it is adjacent to the angle itself. It is one of the two line segments that form the angle, the other line segment being the hypotenuse. Relative to alpha, this leg is called the opposite. It is the leg not involved in the angle measured by alpha. Now there are going to be 6 trigonometric functions whose arguments are this angle alpha. So focusing on this angle, the sine of alpha, written sin for sine and then alpha in parentheses, although sometimes the alpha is not in parentheses, is a ratio of two sides of this right triangle, and that ratio will be the opposite length divided by the hypotenuse length, which we can abbreviate. Now there will be 5 more ratios of sides we're going to compute that are going to give us the 6 trigonometric functions whose arguments are all alpha. So everything we do here on this page will be referencing or relative to this angle alpha. The cosine of alpha is the ratio that is the adjacent divided by the hypotenuse, which we will abbreviate. So you would measure how long the adjacent side is, for example 7 feet, and then divide that by the length of the hypotenuse, for example 10 feet, and you would have 7/10. Now the tangent of alpha is the opposite length divided by the adjacent length. So the length of the opposite divided by the length of the adjacent. It turns out you can also calculate the tangent of alpha by doing the sine of alpha divided by the cosine of alpha. So if you've already calculated the sine of alpha and the cosine of alpha, you can divide them, and that will also produce the tangent of alpha. Keep in mind that the sine of alpha is opposite over hypotenuse, and divide that by the cosine of alpha, which is adjacent over hypotenuse. And you can divide fractions by inverting and multiplying, and the hypotenuse lengths will cancel, and the end result will simply be opposite over adjacent. The remaining 3 trig functions are simply the reciprocals of the first 3 trig functions. So the cosecant of alpha is the reciprocal of the sine of alpha, which is 1 divided by the hypotenuse divided by the hypotenuse. But when you invert and multiply, that gives us the hypotenuse divided by the opposite. You'll notice that the cosecant of alpha is simply the reciprocal result of the sine of alpha. The secant of alpha is the reciprocal of cosine. That gives us 1 over, and the cosine of alpha is the adjacent over hypotenuse, which winds up giving us the hypotenuse over the adjacent. You'll notice that the cosine of alpha is adjacent over hypotenuse, and the secant of alpha is the reciprocal, or the hypotenuse divided by the adjacent. And finally, the cotangent of alpha is the reciprocal of tangent. Therefore, it is the reciprocal of this fraction here, so it is the cosine of alpha divided by the sine. Either way of thinking of this will lead to the conclusion that the cotangent of alpha is the adjacent over the opposite, which is the reciprocal of this fraction. Over here we have a mnemonic. If you sound this out, it reads SOHCAHTOA. It tends to be something easy to remember. And the spelling of this is important. The S stands for sine, and you calculate sine by doing opposite divided by hypotenuse, the O and H. The C stands for cosine, and it's calculated by doing the adjacent over the hypotenuse. And then the T is tangent, and is calculated by doing the opposite divided by the adjacent. So SOHCAHTOA is often remembered and helps keep these ratios straight, at least for the first 3 trig functions. And then you simply must remember that the remaining 3 trig functions are the reciprocals of these first 3 trig functions. Okay, let's put this to use with some numbers. Given the image below, find the sum of the acute angles and the values of the indicated trig functions. Now you may recall from a geometry class that the sum of the interior angles of a triangle always add to 180 degrees. So this angle right here is 90 degrees. That means that the other 2 angles, alpha and beta, must add to the other 90 degrees, which means that individually they must each be less than 90 degrees, which makes both alpha and beta acute. Acute, if you recall, means between 0 and 90 degrees. Now in this problem, we were given the two lengths of the legs. Let's go ahead and put units on these. Let's say these are measured in meters, 3 meters and 2 meters. We are not given the length of the hypotenuse. But if you recall the Pythagorean theorem, we can find the hypotenuse. Let's call it h for hypotenuse for now. We know that leg squared, which is 3 squared, plus other leg squared, which is 2 squared, must be equal to the hypotenuse squared. This is sometimes remembered simply as a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. Well, we can solve for h by squaring 3 and 2 separately and getting 9 and 4 and adding those. That gives us 13. So mathematically, h could be plus or minus the square root of 13. But since h represents a length, let's go ahead and get rid of the minus option and keep only the positive radical. Okay, let's do the first column next. Notice that we are doing the 6 trig functions, all of alpha. The sin stands for sine. That's the name of this trig function. And sometimes this alpha is called the argument, or the input of the trig function. If alpha changes to different numbers, then we get different outputs. Now in this case, we don't know the measurements of alpha and beta. I don't know if alpha is 18 degrees, 20 degrees, 30 degrees, but it turns out it doesn't matter because the sine of alpha will simply be a ratio of 2 of the sides of this triangle. So alpha itself does not need to be measured. We determined that h was the radical 13, and focusing on alpha, in this context, 2 would be the opposite and 3 would be the adjacent. The hypotenuse is radical 13 meters, which if I wanted to decimalize using a calculator is approximately 3.6 meters, confirming it is the longest of the 3 sides of this triangle. So the sine of alpha, whatever measurement alpha has, will be the opposite length divided by the hypotenuse length. So that will be 2 meters divided by radical 13 meters. The units of meters no longer matter here because they cancel each other, making a 1, meter divided by meter. And so the output of a trig function is sometimes considered to be a unitless ratio. And we simply say 2 radical 13ths. The cosine of alpha would be the adjacent divided by the hypotenuse, which will be 3 meters divided by radical 13 meters, or simply 3 radical 13ths. The tangent will be the opposite divided by the adjacent, will be 2 meters divided by 3 meters, or 2/3. Another way to interpret this, of course, is simply that the opposite is 2/3 the length of the adjacent. Now you can also do the tangent of alpha by taking the sine of alpha, which is 2 radical 13ths, and dividing it by the cosine of alpha. I'll do that work over here. So there's the sine of alpha, and divide that by the cosine of alpha, and then invert and multiply. So we have 2 over radical 13, and instead of dividing by 3 over radical 13, I will multiply by radical 13 over 3. And the radical 13s cancel each other, giving you again this 2/3. Now the cosecant of alpha is the reciprocal of the sine of alpha. It's a hypotenuse divided by the opposite. Or if you already have a fraction over here, you simply need to do the reciprocal. So it will be radical 13 over 2. The secant of alpha is the reciprocal of cosine. So do the reciprocal of this fraction, and we get radical 13 over 3. And the cotangent of alpha is the reciprocal of tangent. So instead of 2/3, it'll be 3/2. Now let's shift our focus to the last column, which are the 6 trig functions, but this time the argument will be beta, and beta is in this position. Now relative to beta, the roles of opposite and adjacent will switch. 2 meters will no longer be the opposite, 3 meters will be the opposite, and 2 meters will now be the adjacent. The role of the hypotenuse stays the same. So when I do sine of beta, the sine will still be opposite over hypotenuse, but relative to beta, the opposite leg is 3 meters long, and the hypotenuse is still radical 13. So we have 3 meters over radical 13 meters. Meters cancel. We get this unitless ratio of 3 radical 13ths. The cosine of beta is still the adjacent divided by the hypotenuse, but the adjacent is now the 2 meters relative to beta, and the hypotenuse is still radical 13. So we get 2 over radical 13. The tangent of beta is the opposite divided by the adjacent, and the opposite relative to beta is 3 meters, and the adjacent is 2 meters. And now the remaining 3 trig functions are simply the reciprocals of the first 3 trig functions. Cosecant of beta is the reciprocal of sine of beta, so we have radical 13 over 3. Secant of beta is the reciprocal of cosine of beta, giving us radical 13 over 2. And the cotangent of beta is the reciprocal of tangent of beta, giving us 2/3. Now recall that these two angles, alpha and beta, are said to be complementary acute angles, meaning that they add to 90 degrees. So if alpha was 18 degrees, beta would have to be 90 minus 18, or 72 degrees. If alpha was 20 degrees, beta would have to be 70 degrees. So we can notice some patterns. If alpha and beta are two complementary angles, meaning that they add to 90 degrees, then it will always be the case that the sine of alpha and the cosine of beta will be the same, and the cosine of alpha and the sine of beta will be the same. This means that the cosecant of alpha and the secant of beta will be the same, and the secant of alpha and the cosecant of beta will be the same. Also, the tangent of alpha and the cotangent of beta will be the same, and the cotangent of alpha and the tangent of beta will be the same. These relationships will always be true if alpha and beta are the two acute angle measurements of a right triangle. In other words, if alpha and beta add to 90 degrees. Okay, moving on. Here's another situation where alpha and beta are acute complementary angles. Given that tangent of beta is equal to 0.4, find the values of the indicated trig functions. This time, no lengths are given on this right triangle. However, we know that the tangent of beta is equal to 0.4. I'm going to focus on this entry right here. So we know the tangent of beta is 0.4. And tangent is found by doing the opposite divided by the adjacent relative to beta. So looking in our image, if beta is the angle up here, then the opposite will be the horizontal leg and the adjacent will be the vertical leg. Of course, these roles will switch if I shift my focus to alpha. So we need to just draw any triangle where the opposite divided by the adjacent, as currently labeled, will produce 0.4. Well, this is as simple as converting 0.4 into a fraction, any fraction. 0.4 is 4/10, so we could say that the opposite has length 4, and it doesn't matter what the unit is, 4 inches, centimeters, meters, etc. And the adjacent could have a length of 10 of those units. And then I could find the hypotenuse, and then I'll have a complete triangle. But really, any size triangle with this ratio of 0.4 will be appropriate. Now remember, I said the 4 and 10 could have any unit. It could be meters, feet, yards. So these all represent very differently sized triangles. But we could also do any similar triangle by perhaps cutting these lengths both in half. And we know that 4/10 does simplify to 2/5. So I could also draw a triangle where the opposite is 2 units and the adjacent is 5 of those units. Let's go with these numbers. Let's find the hypotenuse next. We know that the hypotenuse squared will be equal to the leg squared plus the other leg squared. So 2 squared plus 5 squared. That's going to be 29. 4 plus 25. And then take the square root and keep only the positive. So our hypotenuse has a length of radical 29, using whatever unit the 2 and 5 are using. And now we have a complete triangle that we can find all 6 trig functions for each angle, alpha and beta. Let's go ahead and do beta first, since we're already focused on it, and we have the opposite and adjacent correctly labeled relative to beta. So the sine of beta will be the opposite, which is 2, divided by the hypotenuse, which is radical 29. The cosine of beta will be the adjacent, 5, divided by the hypotenuse, radical 29. And once we have these first 3 trig functions, the remaining 3 for this angle are just their reciprocals. The cosecant of beta is radical 29 over 2, which is the reciprocal of sine beta. The secant of beta is radical 29 over 5, which is the reciprocal of cosine beta. And the cotangent of beta is 5/2, which is the reciprocal of tangent beta. Now what we can do is leverage what we learned on the last slide about their patterns for the 6 trig functions if I'm working with alpha and beta are complementary, that they add to 90 degrees, which they always will when you're referencing a right triangle, and the alpha and beta are the measurements of the 2 acute angles. So we know that the cosine of beta should be equal to the sine of alpha. We know that the cosine of alpha and the sine of beta should be the same. Similarly, we know that the cosecant of alpha and the secant of beta should be the same. The secant of alpha and the cosecant of beta should be the same. The tangent of alpha and the cotangent of beta should be the same. And finally, the cotangent of alpha and the tangent of beta should be the same. Of course, we can arrive at these 6 answers by using our reference triangle to the left. Just keep in mind that now we're focused on the angle alpha, and relative to alpha, the role of opposite and adjacent need to switch. So when I do sine of alpha, I will do the opposite relative to alpha, which is 5, divided by the hypotenuse. And we get 5 over radical 29, confirmed right here. The cosine of alpha will be adjacent, 2 divided by radical 29, confirmed right there. Tangent of alpha will be opposite over adjacent, so 5/2. And then these 3 here are simply the reciprocals of these 3. But continuing in terms of ratios, cosecant of alpha is hypotenuse divided by opposite. Secant of alpha is hypotenuse divided by adjacent relative to alpha. And cotangent of alpha is adjacent divided by opposite relative to alpha. So 2 divided by 5. Now keep in mind, I could have done this entire slide using this 4/10, using 4 as this length down here and 10 as this length here. I simply would have had a bigger looking expression up here, and then the ratios of sides might look different, but they all boil down to the same ratios. In the same way that 4/10 and 2/5 both represent 0.4. Okay, moving on. Here's a very generic triangle One acute angle right here is labeled as theta, a Greek letter often used to represent angle measurements. And we are given the information that the sine of theta is b and the cosine of theta is a. Well, relative to theta, the opposite is the vertical leg and the adjacent is the horizontal leg. And we know that the sine of theta, and we're given the information that it's equal to some unknown number b. Well, I can think of this as being b over 1. And then I can think of this in terms of opposite and hypotenuse. This allows me to label two sides of my triangle in such a way that the opposite has length b and the hypotenuse has length 1, so that the opposite divided by hypotenuse will produce, in fact, b over 1, which is just b. We're also told that the cosine of theta is equal to a, which we can write as a fraction, a over 1, and think of this in terms of cosine definition, which is adjacent over hypotenuse. So I can think of the adjacent as having length a, and again, the hypotenuse having length 1. So we wind up producing this generic right triangle where the legs are a and b, and the hypotenuse is 1. Let's take note of the Pythagorean theorem next. So we know that leg squared, a squared, plus other leg squared, b squared, will be equal to the hypotenuse squared, 1 squared. And of course, 1 squared is just 1. And we also know that a is the cosine of theta and b is the sine of theta. So we have cosine of theta squared plus sine of theta squared is equal to 1. This creates what's known as the Pythagorean identity for trigonometry. Cosine squared plus sine squared of any angle. This will work for any acute angle. In fact, it'll turn out to work for any angle theta, even if it's not acute. But sine squared plus cosine squared or cosine squared plus sine squared, doesn't matter, will always equal 1 as long as the arguments theta and theta are the same for both sine and cosine. Now, another way to write a trig function raised to a power, instead of using these parentheses, there can be some confusion. If I just write this, cosine theta, and then put a square, and I don't use parentheses, this can be confusing because it's not clear the order of operations. Should I square theta first and then do the cosine of that angle? Or should I do the cosine of that angle, theta, and then square the result? Well, the answer to this is the latter. So one way to keep this order of operations correct without using parentheses is to change where you put the square. And you put it just after the name of the trig function. So cosine squared of theta is kind of how you read that. And then we can do something similar, sine squared of theta. And here's the Pythagorean theorem written using a syntax that does not require parentheses. And the order of operations is understood to be you do the cosine of theta and sine of theta first, and then you square those results. Down the road, we're going to call this the Pythagorean identity. And it will be true no matter what theta is. It can be any measurement. Both of these angles must be theta for this to be true. Okay, and that wraps up this lesson.